Okay, so what we're going to do now is we're going to try to define a frequency here called the Debye frequency, which is going to correspond to a specific k, this kd times c. And what we're also going to have then is, if we know this, we know that h bar c kd is equal to h bar omega d, which is then kb times some specific temperature, which we're going to call the Debye temperature. Now I can solve specifically here for kd, and I can do that by just dividing all these by h bar c. So I'm going to get then that kd is equal to kb, the Debye temperature, divided by h bar c, and it's also equal to h bar omega d divided by h bar c. Now we also remember that if I have a number per unit volume here, or some little n, that if I've got a volume of a sphere, this is 4/3 pi, and my sphere is in k space, I can say that my r is kd. This is the Debye radius here for my k sphere. This is cube. And I'm going to divide this here by the volume. The volume of k space of some volume element is just that 2 pi cube. Now what I can do with this is I can simplify, and I can right off the bat notice, well, this is just some little n, a number per unit volume. What I've got here on the top is 4. This is 2 times 2 times 2, which is 8. So I'm going to get a half here. I'm going to 3 in the bottom, so that's going to be 6. I'm going to get kd cubed over 6 pi squared. And I know that 6 pi squared n equals kd cubed. Okay. We're still trying to solve that integral for the specific heat. And why we do this so far is we want to figure out what our limits of integrations are, because we're going to try to introduce a substitution. Now, if we remember our integral that we were dealing with, we had Cv equal to 3 h bar c beta squared over 2 pi squared times the integral from 0 to kd of k to the 4 e to the beta h bar ck all over e to the beta h bar ck minus 1 all squared by dk. And this is not a very nice looking integral. So we're going to try to make a substitution here where we have x is equal to beta h bar ck. Now if I do this, I can say that dx is going to be equal to beta h bar c dk. And I can now also take this term of kd, and if I have some that kd term, which I had from before, remember that kd is equal to some Debye temperature over beta h bar ct, then I can say, well, x at k is equal to kd is going to be equal to the Debye temperature divided by T. So what I can now do is I can put some limits in and make a change of variables. So I've got Cv, our specific heat, is 3/2 pi squared of, I'll say beta h bar c squared. This integral from 0 to kd. Now I've got k to the 4, and if I move this around, that gives me x to the 4 over beta h bar c to the 4. I'm going to have e to the x. I'm going to be multiplying here by e to the x minus 1 to the minus 2, and my dk term, which is going to be dx over beta h bar c, and that's equal to dk. So this term can get squished in there and become to the 5. So I've actually got CV is equal to 3 over 2 pi squared. I'm going to get beta h bar c squared, and this term here to the power 4 and this term here together to the power 5, and they have nothing to do with k. So I can pull them out of the integral. Beta h bar c all to the power 5. And now I have 0, and I'm going to replace this kd term with my x limit of integration, which is now the Debye temperature over T. And I'm going to have x to the 4, e to the x, all over e to the x minus 1 squared dx. So we have the specific heat is 3 over 2 pi squared times this beta h bar c to the power minus 3 times kb, the integral from 0 to the Debye temperature divided by T of x to the 4, e to the x, all over e to the x minus 1 all squared dx, where we have to remember what our x is equal to. Our x is equal to beta h bar c k. Okay. Remembering also that beta hc is equal to the Debye temperature divided by kdt, and I already solved for this, but n is equal to kd cubed all over 6 pi squared. Okay, we're going to do a few simplifications here to try to make things a little nicer. We're going to try to substitute a few of these things in. So here's our specific heat. What are some things we can do? Well, one of the things we can do is we can break up that beta hc term. The beta hc term, well, we know that this beta hc, we can try to substitute in our Debye temperature in T. And what we're going to get if I plug this in here is CV is equal to 3 kb over 2 pi squared, and I'm going to get kd T cubed on the top, all over the Debye temperature cubed. This is all over the Debye temperature divided by T. I have x to the 4, e to the x of e to the x minus 1 squared dx. Okay. Now I can work on substituting this guy in here. I've got kd right here. It's cubed already. I've got a pi squared. So I'm going to throw this term in here. And this is going to simplify out real nice. So I'm going to get, if I plug this in, this is like having a 2 times 3 on the bottom here. And what I could do just to make it nicer is move the 3 up to have 3n. And then I can have 3n is kd cubed over 2 pi squared, which is what I've got here. And I've got the kd. So I'm going to put a 3n in. So I'm going to get 9 kbn of T over the Debye temperature all cubed is the integral from 0 to the Debye temperature over T of x to the 4 e to the x all over e to the x minus 1 squared of dx. Now this integral is a little nasty to solve, and commonly if you were just to try to find it at any point, any temperature, you have to plug in your temperature to solve for this. And that would only solve for that exact temperature. We can take an approximation here which says at low temperatures, when T approaches 0, well then this whole term will get larger and larger. So it's almost infinite in a way. So what we could do is we could say, well, what if I had an integral that goes from 0 to infinity? Well, there is an integral that goes from 0 to infinity for this, where we have, well, from 0 to infinity of x to the n, e to the x, all over e to the x minus 1 squared by dx. And this is a special integral. Ends up being n factorial of the Riemann zeta function, or some n, where if we remember that this z of n term is actually equal to the sum from k equals 1 to infinity of 1 over k to the n, whatever our n is here. Now, if we were to plug in our specific n, and this is true for up to, I believe, x, or n equals 4 here. So if we plug this in, we're actually going to get some zeta of 4, which is pi to the 4 over 90. And n factorial is, that's 4 times 3 times 2. This also simplifies out. So what we have now for our specific heat integral is we're going to get 9 kbn of t over theta d cubed of this integral, where we're saying that at low temperatures, this is what it's going to approximate. It's going to approximate 4 factorial times pi to the 4 over 90. And so this, at low temperatures, is actually 12 pi to the 4 kbn over 5 of t over theta d cubed. So the specific heat at low temperatures, using the Debye interpolation method, we can then at low temperatures plug in some temperature, and this is our approximate specific heat. To get an exact value, you would have to integrate this exact temperature all the time, but at low temperatures, this is a very good approximation.